Hello everyone. So we are gonna start our lecture 4. I know it was a little bit break I took, but things have been fine now. So let's start with the machine learning course, which already we have. I think we have done 3 videos already on that. This is fourth video. This is all about regression problems, and it will contains you can say gradient descent optimizers and regulations and logistic regression, which is a type of classification. And in the end, we are going to solve one case study as well. So let's go through it. Machine learning models and training algorithms, as I told you. So why we need to understand this ML models, it's so important, right? See, because we need to find the best appropriate models. Otherwise, if the model is very too small, means too normal, too simple, then the chances that it will not capture the patterns out of the data. Okay, it should be faster, and if it is giving the result after 2 3 days training, there is no point of, right, there is no point of having that model in our system. First checklist done. Select optimal training algorithms. That's what really matters. And effective hyperparameters for those models in which our model is performing good on uh, training, test, and validation set. Debug issues efficiently. If we don't know about the models, how we can debug the issues, right? So we need to understand ML models perfectly fine, because there are high chances that some few errors are related to the you could say you can say even the parameter based errors, right? Parameter based errors which can be solved through the if we have the in-depth knowledge about that particular model we are using, right? Perform better analysis or understanding neural networks. Again, this is like a black box right now. We will talk about this later on. So, few slides will be a summary of the all the key terms which we are gonna study here. Okay, it's not about the in-depth and detailed summary. It's only few bullet points. So, understanding linear regression. It's one of the simplest ML models. That's true. Predicts values based on input features. So, there is a input feature x1, x2, and y1, y2, which is actual values. So again, if it xn, we are going to predict the y hat. So let's say pointer these. So best fit line will be this, in which error will be minimum. And let's say if new point came out x, so we are going to find out through this perfect line. So this will be our new predicted value. Foundation for understanding complex models. So it's a benchmark model, I would say. Widely used in real world applications. Nice. Now there are different types of solutions available there. One is closed form solutions, another one is iteration based solutions, normal solutions, and SVDs. So closed form is simply like a direct computation optimal parameters. We have a loss function, or you can say our equation is already given. We will find out the input parameters x, or you can say weights will be there. So theta and bias, weights and bias will be there. So we will find out those optimal parameters on which the loss will be minimum. And there will be only one step only, okay? So there will be no iteration required for this, and it is very much optimal for the smaller data sets, because if the data set is too big, too huge, it's really difficult to find out the single solution means in a single step, because it will need to capture the all the possibilities out of it. We are gonna see it in detail. Gradient descent. As I told you, it's an optimizer which used to find the optimum solution for that particular equation. And what is that equation? It is the loss function which we need to minimize. So to find out the loss functions parameters at which it will be minimized, we are going to use gradient descent. It's an iterative one. Closed form is a single direct computation. It's an iterative one and gradually tweaks model parameters. It's yeah, there is a learning step concept here. I minimize cost function step by step and eventually converges to the optimal parameter scales better to the large data sets. Key terms. So there are three types of gradient descent optimizers. So it uses batch. First is batch gradient. It uses entire training set in each iteration. More stable but computationally expensive. That's true. Mini batch gradient descent uses random subsets of training data balanced between computation and stability. It took this batch gradient will take complete data set in one go. Mini batch will take let's say if there is 100 instance, so it mini batch will take three or four random set. It can be anywhere. And stochastic is like it will take one random example per iteration. Faster but less convergence. I will show you how. First, then polynomial regression. Linear regression means degree is linear. Polynomial regression means the degree is poly. That means if the equation is like this, x plus 3, anything, just say single degree I want. One, just like one. So x plus 3. This is a single degree. Then that means linear regression will work out. If the equation is like this, x square 4 and y parabola equation, then the chances that it will not capture the this linear models will not capture this pattern. So let's say data is like this, okay, and if we are going to use max to max linear regression will work out like this, but the polynomial will try to make it as much as try to capture this. It depends on the degree or we are using, how much regulation we are using. Otherwise, it will capture all the parameters, and the chances high that it will go to the overfitting. Can fit nonlinear dataset as I have shown you, has more parameters to train, higher risk of overfitting, and requires careful validation. That's true. Detecting overfitting. How we can detect overfitting? So there are concept of learning curves to visualize performance. What is happened? So there is a loss and iteration. Fine, loss and iteration. So when are the chances that our loss will be start from here high, and once it is gone here, this is our validation error, and you can say our loss will be for the training set is like this. So it's difference is too big, right? Too big difference. There are chances that validation error has high, training error is very less. So through learning us, we can see that there is a case of overfitting. Memorization and generalization. We need generalized models always. And how we can do it? We can use regularization. Regularized models we can use. The chances that if we introduce penalty over there, chances of overfitting will be less. So low training error, high validation error. Low training error, as I've shown you, a high validation error. Growing gap between training and validation performance, we can see. Re Regulation techniques, fighting overfitting methods to introduce, reduce overfitting risk, constraint model complexity, improve generation to new data. So in the loss function, we are gonna introduce a new term, which is a regularized term, penalty term. So it will help to reduce the overfitting risk because loss will be, you can say, when there is an iterative approach we are using. So we already have a negative term over here, right? So chances is high that it will not minimize too soon, i- unlike the previous case. Constraint model complexity, improve generalization to new data, balance between fitting data and model simplicity. So L1 is our Lazo, Riz, and elastic net is the combination of these two. I'll show you. Classification, logistic regression. So we have seen linear regression. Now it's about logistic regression. Logistic regression is not a regression. It's a classification because it's based on the probability. So despite the name used for classification, offers probability between 0 and 1. Decision boundary separates classes. So decision boundary, or you can say threshold. So if it is like this, and we have set this parameter that it's above zero point 0.5, then it will be 1, or below zero point 0.5, then it is 0. So that's how we used to separate these two classes, widely used in many applications, foundation for neural network output layers, in which the classification is required, and we are using always and always sigmoid or softmax in the output in neural networks cases. Softmax in binary classification, we used to use the sigmoid function, but in multi-class and softmax, so we are using softmax here. Another case of logistic regression, it handles multiple classes, and it output probability distribution across all classes. Let's say class A, B, C. Probability is zero point 0.6, zero point 0.25, and zero point 0.1. So high chances that uh, output will be A. That's how there are chances that output is A, just because it having the higher probability among all these three, used in many real world applications. Now, real game starts from here. Linear regression fundamentals. Model equation. Y predicted is equal to theta 0 plus theta 1 x1, theta 2 x2 plus theta n till theta n xn. Y hat is equal to theta t x, where x naught is equal to 1. So if I can show you another example to write down in this equation, theta 0, theta 1, x1, theta 2, x2. So these all are bias and weights. Another way to write down is transpose of this theta. So theta 0, theta 1. So it will be like what? N into 1. And what about this? X is also times 1. So x1, x2, x0, x1, x2. And we are considering x0 as 1 and xn. So it will be n into 1, 1 into n, sorry. So 1 and 1, and only n cross n. That's how multiplication will be done here. Or I think it's a column vectors. It should be like this, theta 0, theta 1, and x1, x0, like this. 1 into n into 1, n cross n, so it will be theta 0, theta 1, x1. Yeah, my bad. It's a column vectors, these two. I have not mentioned here, this is not like this will be like this. You can validate on your end. Now it predicts output as weighted sum of inputs plus bias. It will not predict the y hat. This model will predict the inputs plus biases. Right? This theta 0, theta 1, theta x, these all will be predicted by this model. Then we put this in our equation and we got our y hat. Just like life satisfaction is based on this equation, 4.21 plus 2.7 GDP per capita for each unit increase, for life satisfaction increase by 2.7. Yes, even with 0 GDP baseline situation. So this is bias term. This is bias, and this will be our weights. Of each unit, it will be increased. Now we need to find the parameter that best fit training data. So mean square error is one of them, in which, uh, as its name is suggesting, square error. So Let's say this will be our best fit line. So in first go it have predicted this y hat, or actual case was is this y actual. So this will be d difference. Okay, so we are taking d square for one instance, d square for two, and so on, and divided by total parameter, total training parameters m. So that's how we are using it. It will be like y actual square minus y square divided by, and so on, for 1, 2, and divided by m total instance. So first square error, then divided by m, so it will become mean square error. So squaring making more heavily, I mean penalize heavily, because if first error is 2 means 2, so it will make out 4 it here. Okay, it will make out 4 here, so it will enlarging this error condition. For housing price, an error of 50,000 contributes 25 times more to error than 10,000. So 50 square is, we know very well, is 250. I'm taking 25, and its n is 1, so it will be like 1 here. And minimizing MSC finds the line with the smallest average square vertical distance to data points. Alternate solution for these methods will be like this: theta naught is equal to x plus y. It's another way to solve it. Till now we have seen closed form. I think I missed normal equation. Yeah. So normal equation is another thing to write down this thing. So theta naught is equal to xtx minus 1 xty. So theta best is equal to the, how we can implement this method here. So it's a physical signification is that closed form mathematical solution that directly computes optimal parameters and derives from calculus by setting gradient of MSC to 0. For GDP computes theta 0 is this, theta in one step, no it is equal, gives exact analytic solution. That's how we can use, or we can solve closed form equation using this equation. Theta best, NumPy library, linear algebra, inverse, XB, and this is very simple to do it. Another way to write down, I think, multiplication matrix. More numerically stable handles edge cases better, used in scikit implementation using linear regression. Normal equations. Now we will compare these normal equations and SVD approach, and we can see that it will become slow with many features, because this we are solving the equation in one step. As the features will increase, and it will become slow. More efficient but still challenging for very large data set. Physical significance, difficult mathematical paths to same destination. Example, both methods yield identical parameters for GDP model, but SVD works even when data contains perfectly correlated features. So we can see the difference, right? SVD works better when data contains perfectly correlated features. So when to use, in which cases? When the small to medium data set, we can, and which can be fit in, we can use it. When exact solutions are, when computer prediction time matters. This is for all about this normal equation. And limitation is small to medium, it will work out. Poor performance with highly non-linear relationships. That's true. Sensitive to outliers due to square error. This is about linear regression. So linear regression is to be honest, it will not work out non-linear. As it name suggests, it will only work for the linear regression. And it is assuming features are independent. Model assumes linear regression between inputs and outputs. Housing prey may not increase with size beyond certain threshold. That's true. So there are different models out there. This is just a benchmark model, which I think we can consider for the non-linear also. Now, this is the true difference between all these. Closed form equation is any mathematician that can be expressed as a mathematical formula that require a finite number of standard operations to reach the exact solutions. It provides an exact solution rather than approximate or iterative one. It's closed because it gives the answer directly without requiring an infinite series recursion or iterative process. The normal equation is a specific closed form equation used. It's a part of the closed form to solve linear regression problem. It expresses like this. The name normal equation comes from the fact that the error vector is normal to the feature space when the parameters are normal, optimal. Not all closed forms are normal equations, but all normal equations are closed form equations. It's only meant for the closed form. I'm really sorry here. Yeah, in linear regression, the closed form is referred to the fact that we can solve the parameter directly. The static closed form we use the normal equation. The alternative closed form exists like SVD, but they arrive at the same parameter. The key difference in specific closed form is the general form equation, while the normal is a specific formula used to solve linear regression problems. Only consider this thing because nobody will ask you these things. Loss function versus cost functions. Calculate the error for single training examples. If I am considering this y hat minus y, it will be for it will say like loss function. Cost functions for entire training set. First difference. I have shown you this, and there are two types: mean square error and mean absolute error. Those would be like this and 1 by m. I think I don't need to explain this thing much now. Log functions for a single example I have made also. House one actual price is 3 lakhs 250. So it's a loss function, right? So it's a difference between y actual and y predicted. Difference is this. House 2 is this. Now, how can I measure it plus these two things? And house 3 is like this. So how we can predict? So this 3 divided by 3 will be our mean square error. Everything's clear. This was loss function, loss, and now this is mean square error. Another example. Let's see. One, okay, predicted value, probability of being zero point 0.3. So it is different one. It's a different one. And log loss function, we are going to use it here for classification problem. Regression, we use mean square and mean absolute error. So this is a part of the log loss error. Another one is this minus 1 actual. So its formula is like this. Minus y, which is actual, log, you could say 1 and point 5, point p, and plus y predicted into log of 1 minus p. So actual is given here. We have put the value 1.20, zero point 0.1, and 0.11. So another thing, average loss will be 0.47. When training, we optimize the cost function, the aggregate measure. When debugging or understanding model mission specific, we look at the individual losses. Different loss functions create different model behavior. Example, error penalize outliers more than absolute error. So how if it is too far, definitely if we square out, it will do another jump out from the window. Now let's see the gradient descent now. Till now we have seen the closed form solutions which we can use to find out the solution in a single step. But in the iterative approach, it is what I think which will work out in the last data set as well. It's more reliable. So an iterative potential algorithm that's find optimal modules parameters starts with random parameter values and updates them step by step. It will start from here. It's just an example. And learning step is this. And we used to find out and we reached the minimum here. Moves in the direction of steepest descent of the cost function. continues until convergence or minimal or no improvement. If there is no improvement, so it's like this here. This is the minima, global minima. So physical significance is like this. Let's say mountain, like finding our way down a mountain in fog by following the steepest slope, right? We can't see the path, but we can follow the steepest slope. Step getting closer to the valley when you measure. Step size is to determine how quickly you descend. Direction is by the gradient slope at your current position. When the ground is flat, you have reached a minimum. In linear regression, y is equal to theta 0 plus theta 1x, theta 0 and theta 1 as coordinates on a map. The height at each coordinate is the error. The gradient descent finds the lowest point on this error landscape. For the GDP satisfaction, starting with the random value theta 0, theta 1, parameters gradually approach optimal values theta 0, this and this. But it's not an optimal approach to use zeros as random values. We will see it in the upcoming videos. So what are the challenges? See, learning rate matters most. This is an example of very small learning steps, so it will take time to converge. If it's too high, values is too high, it will go random, and our global minimum will be chances are high that we are gonna go high above our global minima. It's too small, very small, slow over convergence, too large, risk of oversetting or diverging. Optimal is large enough for efficient progress, small enough for stability. Makes sense. Terrain challenges. Local mini algorithm can get trapped in a suboptimal solution. So it will, for the optimizer, it will say that it's global minima, but in actually it's a local minima. It has very small gradient, cause small progress. If it is like an flat surface, high chances that it will make small progress because for them it's right. It will like an global minima. Again, conditions are similar, but in actually it is not. Feature scaling and scale feature create elongate balls, making conversion efficient. You can see here, I think not here, but I can show you here. Unfeatured will be like this, okay, like this. In if you are seeing from the front, elongated, so it will take time to here, okay, it will go here. But in actually, if it is like this, featured, every value is featured in one scale, then it will reach too fast now. Like in every different type of terrain, valleys, ridges, plateaus, I told you, convex functions like MSN guarantee a single global minimum. So fortunately, the the mean square error we are using here, it's a single global minimum function. So there are no case of local minima here. I think it's too obvious to say. A minute. Sorry. Housing price prediction with square error. I already told you. Unscaled square footage versus bedroom create elongated room sets. Right. The imbalanced data set also creates a problem. Okay, makes sense. Now let's see mini batch gradient descent optimization algorithm that minimizes cost function using entire dataset per iteration. Like this is not mini batch. It is mini batch. This is mini batch. My bad. This should be batch. Just ignore this line. Okay, don't see. This is batch. Descending by always moving steepest downhill. Each steps bring model parameter closer to the optimal values. Entire dataset per iteration makes sure about these things. Epochs running through one dataset one time. It's called epochs. So this is a gradient vector, direction of steepest increase in parameter space. This is learning rate, which I have told you. That's how we can do it. 2 by m. M is total training instances. X by b again dot t at the rate multi. This will use for the matrix multiplication. I'll explain you the equation. Don't worry about this thing. In the comparison, I have made it. Algorithm navigate multi-dimensional landscape to find lowest point. Learning rates determine step size. Too small, slow convergence. Just right, efficient path to minimum. Overshooting, possible divergence. For convex function, guaranteed to find global minimum. Convergence when gradient approach zero. Each epoch's process entire dataset once. Stable deterministic updates precise gradient calculation. Limitation is that slow for large dataset requires entire dataset in memory. Normalize features for faster convergence. Monitor loss during training to detect convergence issues. Consider SGD or mini-batch variants for large datasets. Now let's see stochastic gradient descent. Concept and significance. What is stochastic gradient descent? Optimization algorithm that uses a single randomly selected instance for each update addresses main limitations of batch gradient descent, slowness on large datasets. Stochastic refer to the randomness in the instance selection. Much faster than batch gradient, processes one instance at a time, can handle huge dataset, only one instance needed in memory, can train on dataset larger than available memory. Randomness helps jump out of suboptimal solutions. I have told you this thing. It will use single only sentence for each update. So if this is a path for global minima exist here, so in case of batch, it will go like this. But in stochastic, it will go like this. Chances high that it will go, it will be topple uh, in these middle means convergence point also global minima can handle huge data set, only one instance needed in memory. That's true. Can train on data set larger than available memory. Randomness helps jump out of subtotal solution, which I have told you here. Patch gradient and use single instance. Gradient calculate from the approximate full gradient. That's how we can implement stochastic. So these are the hyperparameters we are considering here. And we are using learning schedule here. Not we are not fixing the learning step now. Decreasing learning rate over time because once it is near the once far away from these global minima, so we need a huge step. But once it is very near to the global minimum, we want that it will converge very fast here, and chances high that if it is not means if it is not that small, so it will again overshoot this global minima. Locally approach minimum and escape local optima. Yeah, and satellite global minima, similar to similarity annealing metallurgy. So that's how we can do it. T0 is our hyperparameter, T plus T1. This is also hyperparameter. So with the time, if we have set something, so it is too big, it is small, which we have given in case of, so that it will have some values. Denominator will not give throw any error. That's why we have given T1. And with the time, it will decrease, always decrease. It is fixed, it will increase with the time. And so on, it will decrease. And so training instance are suffered similar to implement then which patch gradient descent, SGD regressor, NLT and ETA. ETA is our learning rate. ETA job. Mini batch optimize algorithm that uses small random batches of instances for each update. Middle ground between batch gradient and stochastic gradient. Combined advantage of both approaches. It's true. Faster than batch gradient leverages hardware optimization for matrix operations and particularly efficient on GPUs and specialized hardwares. Less erratic than stochastic gradient descent, more stable gradient estimates than stochastic gradient paths move closer to the minimum than SGD, smoother decentralized tree than SGD. Batch update using all M instance, update using one random instance, update using P random stat, one or two, three instance will be there. Again, it's a middle, you can say somewhat middle between this SGD and batch, nothing new. Typical batch size is 10 to 10,000, depend on data size and available memory, requires supplying obtaining data for best result. Batch size is a key parameter. Smaller means more noise, large means more stable, better hardware, reduces risk of local minima, less hardware, better exploitation. So these are all our hyperparameters we need to discuss. Large data set, batch gradient will be slow, it's true, out of core no, high, hyperparameter will be only 2. SGD is more than 2, fast, fast, yes, yes, fast, fast. So we can use mini batch or SGD for large data set. Batch gradient will always work for the slow. But generally we used to work on this batch gradient generally because if data is 10 to 10,000 rows, I think batch will work out, no problem in that. Mini batch gradient descent is the default in most deep learning framework. Makes training of large neural networks feasible, can handle massive data sets by processing small batches, base for ADAM and RMS probe, balances memory usage with computational efficiency, deep neural network, large scale machine learning, hardware acceleration because deep learning needs is a data hungry activity, so it will ask for only the mini batch. So it's a by default in some libraries. Another thing I have write down here, entire dataset, single random, small batch, take care of these three. Smooth direct path to minimum, noisy, less noisy than HTTP, more efficient than batch. But it is not less noisy than a batch. Okay, it's more efficient than batch. Accurate gradient estimates, guarantee conversion, fast updates, work with any data sets, can escape local minima, hardware optimization, balance of speed and stability, work with large data sets, slow and large, noisy. So it's pros and cons of everything we need to use as our own, you can say, as on our own need. So batch gradient processes m instances per update for a gradient is this. Stochastics process one instance per update and process b instances per update, which is in which b is lesser than total instances, which is m. Computation per update, you can see that it will batches take more time, mini batch in between the stochastic will in last. Processing, stochastic will process fast, batch will be less. It will process m, right? So m will take more time and it will process m take less time. Smoothest, noisiest in between is mini batch. And in one go it will compute m, so it will take more time. It will compute only for b, middle in between middle. Now see this equation in detail. Theta is our the vector of model parameters, weights and bias. Makes sense? Or another way to theta write down w plus b. The learning rate that controls the step size is this neta. Eta, the number of training instances in this m, and the input feature matrix m instance into n features. What are these? M instance means rows, n means columns, you can consider is row into column. Total rows, instances, and total column is features, which is this. And we are taking the transpose. So it will be, let's say it will be 3 into 2. So it will become 2 into 3. Then we are using x theta minus y, which is a vector of prediction error. It's a error, predicted values minus actual values, predicted minus actual. Now this xt is gradient of the cost function with respect to parameters. This is loss function, sorry, this is cost function, and we are multiplying with xt difference, and we are multiplying this xt, then it will become the gradient of this cost function with respect to the parameters. That's true. That's completely true. And 2 by m is the scaling factor that average the gradient across Wallenstein. That 2 comes from differentiating the square error. There will be a 2, right? So if I differentiate this mean square error, so 2 will become from here after differentiating. Same goes with the stochastic difference, which simply is, I think it's somewhat very similar, 2 by n, but there is no 2 by m is will be eliminated because we are taking m, so m will become 1, otherwise things are same. You can see, makes sense, right? And I is means we are using single instance, so I will be the ith instance of the data set. Everything same, just b we are considering here. Same like batch gradient. The key method of doing this is the number of instances used to estimate the gradient. All instance for batch, a single for stochastic, subset for mini batch. That's it. That's it only about this mini batch or gradient descents. What are the learning curves? So this plot showing training error validation as a function of training set size. Training set size, cost will be or error will be minimized with the time. It will be like this. For detecting underfitting and overfitting, I have already shown you. Visually represents model's learning progress and generalizing ability. Both curves reach similar high plateau. Underfitting means this is training, and also the validation will be like this, and the error is too big. Then it will be underfitting case. Adding more data doesn't mean help, and model structure is fundamentally inadequate for the problem. Using a linear regression model for the quadratic data, it will not capture the quadratic, I mean, quadratic rate problems. Large gap between training error and validation error. Overfitting. Low training error, small gap between training error. This is the optimal case. When this is like this, it can be considered. Examples are here: 1 2 degree, 300 degrees. So great, you can see that this high degree is capturing very well this random data set, right? But this red line linear regression is not able to do it. Training set size, we can see that error is getting lesser here, and at one time they will merge. Why is it happening that this validation error is less? Because for smaller data set, our models will work fine, but as the data set increases, like capturing the same, making it the generalized model which capture the every pattern out of it, it's a huge deal, right? Then it's not able to make it like in the first cases, in the first few example instances, it can, but the next one it can't. Bias variance, decomposition, generalization error, bias plus variance, and irreducible error. Bias, what is bias? Underfitting. Variance is overfitting. Error from incorrect assumption in the model. Y actual minus Y prediction. It is bias. Error from sensitive to small precision in training data. If the input is here, little bit inflation, but data is you can say giving so much you can say error. Then the high chance that our data is here somewhat here. It is not focused. Modern generative capture true relation data, high training error, high validation error using a ruler to measure curved surface. To increase model complexity or add more relevant features. Error from sensitive small fluctuations training data. Model tendency to learn from noise rather than signal. Low training error. High validation error. Memorizing test answer without understanding principles. More training data. Regulation of simpler model. Error from inherent noise in the problems. Fundamental limitation of predictability at the data. Static noise in data signals. Improve data quality or collection methods, which we can't do, right? This can be solved. Bias can be solved more. I mean, more data. I mean, increase model complexity, we can solve it because problem is not even solving by this underfitting, but overfitting can be solved using the more data or regularization we can do. High bias, low variance, simple model. Low bias, high variance is complex models. Is when this low bias and low variance happen, the best model means it's given the correct value, it is not underfit, and low variance means it's not overfit. So optimal complexity is balancing between these two. Now regularized model. A regularized version of linear regression that penalizes the large coefficient adds a penalty term to the cost function, sum of square weights, mathematical formulation, MSc theta plus alpha 1m theta square. So it's already having the cost function, but we are adding here one sum of square error, means alpha is our hyperparameter here, and what happened here? So shrink coefficient towards zero, but rarely to exactly zero. Makes the problem non-singular even when X is not invertible. Constraint way to lie within an n-dimensional hypersphere when pitch are correlated. When the model shows signs of overfitting. When you want to reduce model complexity while keeping all features. When you suspect many features contribute a little bit versus a few features contribute a lot. Then we can use it. There are direct closed form gradient descent. I don't need to explain this now. Now let's talk about this alpha hyperparameter equivalent to if this is zero, then we have the no regulation case because the MSC will be there. If in infinity all weights are approaching zero under fitting case, optimals so that it will add some penalty over there. Another thing is model filtering data closely, potentially overfitting. High alpha model becomes simpler approach, horizontal line at mean. And optimally capture true pattern without fitting data. Regulation is scale dependent. Use standard scale or similar processing. Simpler, right? That's true. That's work right. Lasso is it was squared. The difference is only single term. You can see only 2 alpha where it is 1 by beta square. Single degree we use to call it and also L1. So we use absolute weights of weights instead of square weights. This is square weights, theta square, and here we use absolute weights, theta. Automatically eliminate irrelevant features by setting the weights to 0. Produces model with few known coefficient. The constraint weights to lie within n-dimensional rhombus. Optimization reference refer reaches another constraint region, setting some weights to exactly 0. So no weights approach but rarely equal 0. L2 has no corners, that's true. And it is not possible to do differentiation at 0. When you have many features, possibly more than samples. When you need to identify most influencer variables. When you want to reduce model complexity drastically, few features contribute significantly less. Reaches axis before converging to final solution, bounces around optimum due to non-smooth construction, requires decreasing learning rate for convergence. Critical before applying lasso like all regularized models. Minimal regulation, few zeros, many zeros. Find optimal alpha. Less stable than reach for feature selection with correlated predictions. Now this Elastic net is considered the correlated combines L1 and L2 penalties. The combination of these two. So plus this is L1 term, this is L2 term, and R is our high parameter here. Feature selection and sparsity, we can use stability with correlated features. Solves less erratic behavior when features more than samples. Handles group of correlated features better than LSO alone. More stable variable selection than pure LSO. When to use net. High dimensional data with correlated feature when you want control sparsity without complete elimination of correlated variables. When both feature selection and multi-correlative handling are needed, is a safer default than either ridge or lasso alone. Constraint region between hypersphere and rhombus. Combine corner seeking behavior L1 with stability. So these are some geometry interpretation, but we need to make sure that this is a combination of lasso and ridge. Lasso is used to find the feature selection and sparsity, feature selection and stability with correlated features. When both feature selection and multi-correlative are needed, right? When you want control sparsity without complete elimination of correlated variables, often preferring practice over pure ridge or lasso. And there's a parameter alpha and R, genomics, finance, and there are many applications over there. Early stopping concept is basically when there is stop training as soon as validation error starts to increase. Model complexity increases with training time. A beautiful free lunch for regularization. Implicity limits model complexity without modifying the cost function. During training, model first learns general patterns, then noise. As training progress, training error continuously decrease, validation initial decrease, then increases U curve. So the minimum of validation represents optimal trade-off between bias and variance. I think I have made some graph here also. Let me show you. So validation error is first decrease, then it will increase like this. So this will be our optimal solution. So we will stop our solution here. No hypermetric tune, unlike Ridge or Lasso, computationally efficient, can reduce training time, applicable to any iterative learning algorithm, work with any model type, require validation set, stochastic algorithm produce noisy curve, need to store best model parameters in memory, large neural networks, training is computationally expensive when you want regression without explicitly modifying the cost functions. Logistic regression, a classification algorithm that estimates the probability of an instance belonging to a particular class. Despite its name for classification rather than regression, one of the most widely used algorithms for binary classification. I have told you this thing. If probability is this more than this, then one otherwise else. So this is our decision boundary, provides probability estimate, not just classification. Coefficients indicate feature importance and direction of influence. Makes sense, right? Creates linear decision boundary in feature space, basis for many advanced models. Maps any real value to range this suitable for probability. Sigmoid is for binary classification. Approach 1 as z increases, approach 0 as z decreases. 0 is 0 from the decision threshold by default. So it will be like this. Okay. So when it's 0, this will become zero point 0.5, right? 1 by 2.5. When it says z z is increasing, so it's will infinity. So 1 by infinity is 0, so it will be 1, but it decreases, so 1 by this, it will become big. Number overall become big, so it will become 0. Cost function name is log loss. Mean square error for the regression and log loss for the binary classification minus 1 by m. And here we are using y hat actual, so predicted plus 1 minus yi log 1 minus p by I. It's too obvious, right? Heavily analyze confident but wrong predictions. Right from maximum likelihood estimate, convection again to look over minimum. No closed form solution exists for these. Prediction disease presence based on symptoms, spam detection, KD scoring, customer churn, where two classes will be there, whether that person will leave or not, KD score, it's fraud or not, spam or not, text classification we can use Fast training probabilistic output and works well with the sparse data. Sparse data is like this: 1 0 0 0 0 1 0 0 0 1. That's like this sparse matrix will very work well. Linear decision boundary assumes feature independent struggle with the imbalanced data. That's why it's linear, right? What are decision boundaries? Boundaries in feature space that separate different classes. In logistic regression, points where the predictive probability is this. So if it is too big, right, too big, then it will 1 plus c minus x is 2 increasing. So it will increase to the 1. If 2 decreasing, it will 0. So it will be like this, approach to the 0, not 0. And zero point 0.5, if it is more than 0.5, then probability is 1, and it is like a boundary layer it have created. Two feature forms a line, forms a plane, hyperplane, and dimensional spaces. So this is for two feature I'm considering. But in the case of this 2, 3, we can't even visualize this thing. How model makes decision, help identify reasons of uncertain potential classification. And different model care different boundary set. That's true. Logistification always linear boundaries. Decision tree axis parallel boundaries. SVM with non-linear kernel, complex curved boundaries. So logistic regression means these values are this. So it will create a form like this: one class, two class. Equation is like this: x1 and x2. Linear space of equal probability prediction indicate models confident across different features, allows contour steep probability gradient, gradual transition between classes. That's how we can see the decision boundaries. Decision boundary, let's say 1.65. So when width is less than this, prediction non-Vargiga, otherwise Varginica. That's how we did it in this code also. Identify where model make mistake, move boundary balance precision recall, verify boundary aligns with the expert knowledge, identify unusual samples near boundary, suggest new features to improve separation. So optimize segregation, generalize some logistication to handle multiple class directly. Multiple class, it can be 3 or more than 2. And also called multinomial logistic regression. Output varieties across all classes, native multi-class classifier. Each class K has its own parameters theta K. Its formula is like this. Okay, x1 x2, I think like this, ax3, and priority will be like this. We are calculating, and the whatever is the argmax means point. I have shown you, right, 0.5, 0.05, A, B, C. So whatever having the you can say max. That's what we are doing here. We are picking this classification. Model relationship between all classes simultaneously provides confidence level for each class prediction, creates linear boundary between any two class, more efficient than training multiple one versus rest classification. In the last video which I have told you that one versus rest means it will uh one one O means, let's say, O1, O3, O4, right? So it will make small set with O1, O3, O4, O2, O3, O4. Whoever will win, it will give that value. So we generally use one for all, one versus this was one versus sorry, this was one versus one, and one versus rest is predicting this and checking for each value, one versus rest. But it is more efficient than those and derived from maximum likelihood from category or distribution. That's how we can do it. And log logs function for the binary. Multiple is cross entropy. I have shown you the example. E2 E10.1 is this row scores from model, and then we are putting this value in this 0.65 for class 1, 10, 0.3, 0.11. That's how we calculate. Each class represents predicted class and linear distance boundary between any two classes, covered probability contour within each region. At three-way boundary point equal 33% probability for each class. Categorizing text into multiple topics. I think this I already explained in the last video, this classification in detail. Now let's see if you some question answer which can be asked. Which linear regression training algorithm can you use if you have a training set with millions of features? SGD or mini batch? No way, batch. Suppose the feature in your training set have a very different scale, which algorithm might suffer from this and how, what can you do about it? GD-based algorithms suffer because feature with large scale dominate the optimization process, right? And also scale sensitive sensor penetration. So standardized feature, zero mean unit variance means one variance. Standard deviation is one and zero win. Like this, zero win and standard deviation is one. Using standard scaler. Can the gradient descent get stuck in a local minimum maintaining? No, it can't be because it's a convex function always. Do all gradient descent lead to the same order provided you let them run enough for convection? Like yes, they converge to the same solutions. For convection, different you may find different local minima. Suppose you use batch gradient descent and you plot the stochastic validation vary at every epoch. If you notice the validation consistently goes up, what is likely go up? How can you fix this? And you plot the validation at every epoch. If you notice the validation is okay, it is going like this. Model is overfitted. That's true. Difference is too big. Add regulation, reduce model complexity. Stop early. Yeah, we can do it. But slowly make SGD converge by using a decreasing learning trail. Yeah, we can do like this also. Suppose you are using polynomials, you plot the learning curves and you notice that there is a large gap between the training error and the validation error. So there is a validation error and this is our training error. What is happening? What are three ways to solve this? Number one is the model is overfitting. Then we can use get more training data. Yeah, reduce polynomial degree and add regularization. If it is underfit, then we need to use the better models. Why do you want to use rich lessons instead of plain regression? To reduce overfitting, which is correlated to ensure numeric stability. Lessons instead of to perform automatic feature selection, coefficient can be exactly zero. Fine, it will reduce the features. It will reduce when features are correlated. Yes. Suppose you want to classify feature as outdoor, indoor, and daytime, nighttime. So do you implement two logistic regression as or one? Okay, one feature outdoor, indoor, daytime, nighttime. So do you consider two registration classes as or one software registration? Two separate registrations because they are independent attributes, not mutually exclusive classes. That's true. Suppose you are using ridge regression, you notice that the training error and the validation error are almost equal and fairly high. Would you say the models are from high bias or high variance? So to increase the regulation of parameters. So it is happening right now. It is the case of underfitting. Yes. And this that's how we can implement software regression without list hopping, without using SQL library. We have implemented this import np and a model split simply. Then we have softmax function, which is like this: z np dot sum total, and it will consider the ex of ex1 plus ex2 ex3. Now we need to find out this ex1, or you can say z. This is for cross entropy minus np.log. Then we can find out these values. And then we got our results. So this was all about the regressions problem and how we can train the model. In the next video, we are gonna solve the case study, and this will be very interesting one because in which we will implement each and every gradient descent. We can see the difference of this gradient descent, how it's performing, and we will create a contour before feature scaling and after feature scaling, and we will also do the softness problem, and we will implement the regularization Minsky, and we will see the difference among these. So it's an interesting video coming up. So thanks for watching, right?